For the first problem, because light bulbs A and B are in series, all the current that flows through one will flow through the other. Therefore, the correct answer is C. Each conducts the same current. Number 2, if we place two long wires parallel to each other and the current through each wire is in the same direction, they will attract. Now, you can memorize this rule, or you can realize that the magnetic field that's produced by, say, the lower wire at the position here will be out of the board. And if you use the right-hand rule, so you cross the current direction crossed with the direction out of the board, you will find a force direction towards the other wire. And by Newton's third law, the force on the other wire will be in the opposite direction. Therefore, the two will attract. Problem 3. In the circuit shown here, you have two light bulbs that are in series when the switch is open. When the switch is closed, the resistance through this wire is basically 0, so all the current will flow through this and none of the current will flow through the light bulb. This will in essence reduce the resistance of the entire circuit, and since the resistance of the entire circuit is less, there will be more current flowing through the battery, and this of course is in series, so the current through A will increase, therefore its brightness will increase also. Okay, problem 4. Consider an infinite conducting wire along the z-axis conducting current in the positive z direction. At the point x, y, z equals 1, 0, 0, what direction does the magnetic field point? In this case, it's just a problem in remembering the right-hand rule for the coordinate system. So I'll write an x, y, z coordinate system here. Now the wire's along the z-axis and it's conducting current in the positive z direction. Now if you use your right hand to determine the direction of the magnetic field at this position, which is about x equals 1 and y and z equals 0, you will get a direction for the magnetic field pointing in this direction by the right hand rule. That is in the positive y direction. So the correct answer is C. Problem 5. A negatively charged particle enters a region where the magnetic field points as shown. The arrow is the direction of motion. In what direction is the magnetic force? Here again is the right-hand rule. So you must take the direction of motion to the right and cross that into the direction out of the board. When you do that, you get a vector pointing down. But if you remember that the particle is actually negatively charged, the actual direction of the force must be the opposite direction. So the correct answer is A, or up in the plane of the paper. In problem 6, we have more resistors added in parallel. And as we add more resistors in parallel, of course, the number of paths will increase, which will decrease the resistance. You can also use the formula. If you remember the formula for adding resistors in parallel, you add the inverses and then you take the inverse of that. And of course, as you add more inverses, you get a larger number, and when you invert a larger number, you get a smaller number. So the total resistance decreases. Problem 7 gives you a diagram of a magnetic force and a velocity and asks you what is the direction of the magnetic field that causes this force. Now, if you remember in the cross product, since the magnetic force is equal to the charge times V cross B, the force must be perpendicular to both V and B. But you can see in this diagram the force is not perpendicular. Therefore, this is actually not a possible direction. So the correct answer is E. This problem number 8. When you move the north end of a magnet towards a loop, what will be the direction of the induced current viewed from the meter side? To solve this problem, first we're going to define a direction of the A vector, and I'm going to define the A vector pointing towards me so that the initial flux is positive. As I move the magnet towards the loop, of course the strength of the magnetic field will increase here and we get an increase in flux. The induced magnetic flux must be negative then. that requires a magnetic field pointing in the opposite direction of motion. So that would be the induced magnetic field would be that way. The only way to get that is to get a current flowing in this direction by the right-hand rule, and that is clockwise. Problem 9. You have 3 circuits constructed of identical batteries and bulbs. Rank the brightness of the bulbs. First, we can compare pairwise some of these. Now, A compared to B and C, because B and C are in series, the resistance in this circuit will be greater, therefore less current will flow through this circuit because the resistance is greater. That immediately tells you that A is brighter than B, which equals C. C must equal B because the same current flows through both. We can also look at compare D and E to A. Because D and E are both at the same voltage, the voltage difference between here and here is the same, the amount of current flowing through them must be the same. So D must equal E. But you notice that the voltage here is the same as the voltage difference here. So in fact, D equals E equals A. The correct answer then is B. Final problem. You are shown 2 cases here where a battery is connected to a box which contains identical resistors. So A and B are identical. The battery provides an EMF which is equal to V. Which box draws more current? Clearly, this box has more resistance because this has, first of all, fewer paths, and it has 2 in series. Each of these paths has the same resistance as one of these, but in addition, these are in parallel, so the resistance of this is clearly less than the resistance of just one of them, which is less than these. So clearly 2 is less, 2 draws more current than 1. So the answer must be either D or E. Now, as you'll see, I'm going to argue that the correct answer really is E. Why is that? Because if you consider the resistance of number 1 would be twice the resistance of any one of them. But the resistance of box 2 would actually be R over 2 because you've got 2 resistors in parallel. So it has half the resistance of 1. And the ratio of these is clearly 4. So number 2 draws 4 times as much current as number 1. In this problem, you're only asked for the current through the R1 resistor. You do not have to completely solve the circuit. But in order to determine that, notice that R1 is part of a parallel circuit of resistors here. So we need to determine the voltage across R1 in order to determine its current. The way I'm going to do that is I'm going to draw an equivalent circuit first, where I'm going to add these 2 resistors in parallel. So we have R3 here, and then we have an equivalent resistor here, and R3 is 3 ohms. To determine this, we must add these 2 in parallel. So 1 over R equivalent is 1 over 1 ohm plus 1 over 2 ohms, which is 3 over 2 inverse ohms. And this, of course, implies that R equivalent is 2/3 of an ohm, or 0.67 ohms. Now then, to determine the voltage drop across the R1, I use the fact that the voltage drop across the equivalent resistor in this circuit will be the same as the voltage drop across R1 in that original circuit. So using the fact that this is a voltage divider, we know that the voltage drop across this resistor is proportional to its resistance, right? Because V equals IR. The total resistance is 3 plus R equivalent. This implies that the voltage drop across the resistor number 1 will be the 0.67 ohms divided by the total resistance, which is 3 ohms plus the R equivalent, or 3.67 ohms, times the total voltage, which is 0.5 volts. That is 0.091 volts. That's the voltage drop across the R1 resistor. Now we can determine the current through that resistor just by using Ohm's law. So that should be V1 over R1, which, since it's just 1 ohm of resistance, it's pretty straightforward calculation. Problem 2 has a proton and an electron both traveling at 5,000 meters per second into a region of constant magnetic field. The particles are you're told that they move in circles, and the radius of the proton's motion. So first, what is the strength of the magnetic field? In this case, we can use the formula for the radius or the cyclotron radius directly. If we solve that for the magnetic field, we get mv over qr. Now in this case, we're given the information about the radius of the proton. So we're going to use the mass of the proton here. Its charge is E, and the radius of its motion. So we use the mass of the proton, the given velocity, the charge on the proton, and the given radius, and that turns out to be this value right here, which is about 350 microtesla. Next problem. What is the magnitude of the force on the proton? Now there are different ways to solve this problem. What I used is the formula for the magnetic force, and since the velocity and the magnetic field are perpendicular, this just reduces to this formula right here. Which turns out to be 2.78 times 10 to the minus 19 newtons, or 2.8 to 2 sig figs. You can also use the formula F equals mv squared over r, where you have to use the mass of the proton, and then you can use the radius and the speed given to get this formula also. This is the formula for the centripetal force. It also gives the correct answer. To determine the radius of the electron's motion, again we can use this cyclotron radius formula, but here we'll use the mass of the electron and the charge of the electron, and of course the magnetic field, which is already known. Now this, since we know the radius of the proton's motion, we can also write this way, because it's proportional to the electron, to the mass of the particle. So if I write it this way, I can also get the answer, and I just need the ratio of their two masses times the 15 centimeters. And this turns out to be 8.18 times 10 to the minus 5 meters, which to 2 sig figs is 82 microns. The last problem here asks you to determine the if the direction of the motion of the proton is clockwise or counterclockwise. And the best way to see this, I think, is just to draw a simple diagram. Here, these dots represent the magnetic field. It's coming out at you, so you're actually looking south. If you remember, the magnetic field is pointing north. The course of the motion of the proton will be a circle. Now let's pick a random direction. Let's imagine that it's moving this way and ask what direction force would that indicate. Well, if we take the right hand rule, use the right hand rule to get the cross product between the velocity and the magnetic field, which is pointing out, we do get a vector down, which is the correct direction for the magnetic field. That's the magnetic force that's towards the center, and that motion you can see is clockwise. Okay, the first part of this problem asks the magnitude of the magnetic field produced by wire 1 at the point A. So this wire here at point A, which is halfway between wires 1 and 3. This is just a direct application of the formula that the magnetic field produced by a wire is equal to mu naught times the current over 2 pi r, where r is the distance of the point from the wire. So the problem here is just to determine the distance r, and r here is the distance from here to there. That r is just going to be half the diagonal here. The side of the square, if you think of it, this actually makes a square, so this diagonal is the square root of 2 times one side. But it's only half of that, right? So it's the square root of 2 over 2. So we can stick that in there, and we just get mu naught I, the square root of 2 over 2 pi s. This can also be written as mu naught I over s pi, the square root of 2. Now, part B asks the magnitude of the magnetic field produced by wire 2. If you look at the diagram, let's take a look at that. You can see that wire 2 is the same distance from point A as wire 1. Therefore, the magnitude of the field produced by this will also be the same. No, we're not asked about the direction here, just the magnitude. So the magnitude of B2 actually equals B1. It's the same as the answer to part A. In part C, we're asked the magnitude of the net magnetic field produced by all the wires. Let me reproduce the diagram here. So we have a field coming out, current coming out, current coming out, current going in, and this is the point A. If you think about it, let's consider the directions of the fields produced by 1, 2, and 3. The direction of the field produced by 1 is out in this direction, and that produced by 2 is down in this direction, and that produced by 3 is opposite the direction produced by 1. Now, the magnitudes of all these are exactly the same because they're all the same distance from point A. So that means B1 plus B3, for example, equals 0. They cancel. So B net is actually just equal to B2, and we know that that magnitude, we've already figured it out, it's the same as B1. Again, same as the answer to part A. The last question is, what's the direction of the magnetic field produced by all the wires? So let me leave this here and let's look at this diagram. I've already shown that the fields produced by wire 1 and wire 3 cancel, so all that we're left with is the field of B2. So in fact, the magnetic field the net magnetic field is the same as the magnetic field B2, and we can see that its direction is toward wire 3. In this problem, you have a square wire loop that is inside a uniform magnetic field that flips around. Okay, so let me draw some axes here, x, y, and z, and the description of the loop puts the square wire loop in the zy plane. It's on an axle which lies along the y-axis, so that's along here, so that it can be rotated. So in a period of 105 milliseconds, it's rotated once around that axis. And you're to determine the magnitude of the EMF. You don't have to determine the direction, just the magnitude. So the magnetic field, we see points along the plus x direction. Okay, for this problem, let's define an area vector. I'm going to define an area vector which also points initially along the x-axis. And what's going to happen as the loop rotates, the loop will rotate around, and the area vector, which originally was pointing this direction, will end up pointing in the opposite direction. Where A1 is minus A0. So the final area vector is actually negative of the initial. So let's apply the law here. So the EMF, and here we're just interested in the magnitude of it, will equal the ratio of the change in flux over the time there, which is the final flux minus the initial flux over delta t. The final flux will be B dotted into A1 minus the initial, which will be B dotted into A0. That's divided by delta t. Now, we can use the fact that the final is actually negative the initial. So the negative signs both cancel by the absolute value, and also note that B dot A is a positive number. The cosine between the angle, of course, is 1. So you just have this expression for the flux. So let's evaluate that. 2 times, we're told the magnitude is 5.2 Tesla. The area, of course, it's a square, so it's 25 centimeters square. And we're told the time, 105 seconds. That evaluates to about 6.19 volts, or 6.2 to two significant figures.